Okay, we're going to take a look at improper integrals, which are integrals that may approach positive or negative infinity, or possibly they have a vertical asymptote somewhere on their interior. Up to this point, all the integrals we take are of continuous functions over closed intervals, so there have been no asymptotes, and we haven't had anything that maybe goes out and approaches infinity. If we have either of those cases, we call this an improper integral. And it turns out, even though it might not seem intuitive, if we take the limit or an integral that goes out to infinity, it's possible that there's still a finite area bounded underneath the curve. Let's take a look at the integral from 1 to infinity of 1 over x squared. All right, so we have this region here from 1 out to infinity, and you can see the curve gets closer and closer to the x-axis. We want to find out if that area bounded underneath there is going to be some finite value, or maybe it's infinite and just gets bigger and bigger and bigger. Okay, so if we're ever dealing with a limit of integration that approaches positive or negative infinity, we need to replace that with a constant, or b, or a, or whatever you might want to use there, and take the limit of the integral. So we're going to take the limit as b goes to infinity of the integral from 1 to b of x to the negative 2 dx. And we can compute the integral the same way we typically would. We're just then, when we evaluate, going to take the limit as b approaches infinity. So limit as b approaches infinity of negative x to the negative 1 from 1 to b. Plug in our limits of integration. So we know that 1 to the power of negative 1 is 1. And as b gets larger and larger and larger, well, negative b to the negative 1 is negative 1 over b. So that's negative 1 over infinity, which is 0. So this thing approaches 1, which is kind of a cool result, that we found the area underneath the curve from 1 to infinity equals 1, meaning even though we go farther and farther out to the right, getting bigger and bigger and bigger, the area underneath that curve just gets closer and closer to 1. If this is the case, if we take that integral of a function that approaches infinity and it gives us a constant, we say that that integral converges. In this case, it converges to 1. Let's take a look at this. Integral from 0 to 1. Well, if we plugged in 1, we would get 0 on the bottom of our expression there, so we have to replace 1 with something else and take a limit. So in this case, we have a vertical asymptote at x equals 1. We're looking at the integral from 0 to 1. So even though the function tends up towards infinity, it's possible that there's a finite area bounded in this region. So we take the limit as b goes to 1 from the negative side, because since our limits of integration go from 0 to 1, we're approaching that 1 from the left, of the integral from 0 to b of our function. So we can go through taking the antiderivative, and it might be useful to do some of this work, taking the antiderivative a little separate from the limits of integration, and then once you've found your antiderivative, go back to putting the limits on. Okay, so we have 1 plus x in the numerator, so we can split this into two fractions, 1 over root 1 minus x squared and x over root 1 minus x squared. Dealing with the one on the right, we can let u equal 1 minus x squared, so du is negative 2x dx, or negative 1/2 du is x dx. The left side we can figure out directly, that's the derivative of inverse sine. Take the antiderivative on the right-hand side, and substitute u back in, and now we can go ahead and put all of our limits back on. So we're evaluating from 0 to b, as b approaches 1 from the left-hand side. Plug in our limits of integration. Keep in mind that we're still evaluating this limit as b approaches 1 from the left-hand side. And so we go through each of these pieces one at a time. As b approaches 1 from the left-hand side of inverse sine, so that's inverse sine of 1, that'd be pi over 2. Plug in 1 into that root 1 minus b squared, and you end up with 0. Inverse sine of 0 is 0, root 1 is 1, and we end up with pi over 2 plus 1. So it turns out the region bounded here turns out to be finite. This converges to pi over 2 plus 1. All right, now let's take a look at the integral from 0 to 1 of dx over x, which is the same as 1 over x dx. So we'll take the limit as b approaches 0 from the right-hand side of the integral from b to 1 of 1 over x dx. Take the antiderivative, and we get natural log of absolute value of x. Plug in our limits of integration. Natural log of 1 is 0. Natural log as we approach 0 from the right-hand side, natural log as we approach 0 from the right-hand side is approaching negative infinity. So we have 0 minus negative infinity, which is infinity. So it turns out the area bounded from 0 to 1 of 1 over x is infinite. In this case, we say that the integral diverges. So if the area underneath is unbounded, getting larger and larger, we say that it diverges. Okay, we've got the integral from 0 to 3 of 1 over x minus 1 to the 2/3. And if we examine that interval, 0 to 3, we should realize that if we plugged in x equals 1, we would be dividing by 0. So we have this asymptote. So let's go ahead and split this thing up. We can take the limit as b approaches 1 from the left, from 0 to b, plus the limit as c approaches 1 from the right, of the integral from c to 3. If we take the antiderivative, now we'll plug in our limits of integration and evaluate. We get 0 and 0, and we end up with 3 plus 3 cubed root of 2.